Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I will begin with a few caveats. First is that this is a biased guided tour through the basics. By biased, I mean it reflects my personal biases. So it's what I think is the best introduction. So I apologize to everybody in advance for omitting your favorite result. I probably will. I should also say that this talk, so Milan told me that the audience is going to be, you did tell me, that the audience is going to be not really theory, and so I prepared something which is rather general and trying to address a non-theory audience. So for the theorists in the audience, you might think that I'm saying very simple things, and yes, indeed I am, but this is only the basics. So hopefully I'll hint at some of the deeper things. Okay, so let's begin with some history. The history of lower bounds for data streams begins actually with the very first paper on data streams, which is by Munro and Patterson. So they were looking at the median finding problem, actually selection more generally. So you have a stream of m values. I shall use m throughout the talk for the length of the stream. And their result, at least their main result, was that using p pulses, this can be done in m to the 1 over p space. The tilde indicates that I'm ignoring certain log factors. The theta indicates that this is both a lower and an upper bound. So in fact, they did prove a lower bound, right? And you will find this beautiful piece of prose in their paper. And I put it up there actually to emphasize to you that I think writing a good paper is a work of literature, and I think we lose this these days. It's so nice to see prose like that. All right. So there is, however, if you look carefully through what they're saying, they're talking about an adversary argument, and these arguments have a major weakness, which is that they're making an assumption. The assumption here is that the algorithm only stores values from the stream to solve the problem. Right? Now, in general, you could imagine doing some arithmetic on the values as you see them, and why not? Maybe that helps. So fast forward about 20 years, this gets us to the modern history of the problem. This seminal paper really by Alon, Matias, and Segedi probably made data stream algorithms an important topic of study in theoretical CS. They did many things in here. Among other things, they introduced the frequency moments problem, which you hear a lot about, which Graham also mentioned in his talk this morning. The paper introduced several important algorithmic techniques. These are still relevant. I won't talk about the algorithmic techniques, but most importantly, from my point of view, they laid the foundations of data stream lower bounds, in particular by recognizing the central role of communication complexity. And communication complexity gets around this issue that I brought up earlier with adversarial type lower bounds, that it makes no assumption about what exactly the data stream algorithm stores, or for that matter, how it computes what it stores. Okay. So most of this talk is really going to be about communication complexity and what role it plays in data stream lower bounds. So I'm going to talk about very simple communication games and what they imply. And you'll see, I hope, that proving lower bounds like this is actually fun. It's a nice game. All right, so why is communication complexity important? Well, there's this obvious little reduction which says take any problem on data streams. You can take your stream and split it up into chunks like that. Give each chunk to a player, and now you have a multiplayer communication game. Of course, you could have just two players. The chunks don't have to be equal in size. There are situations where it's advantageous to make them unequal in size. And having done this, a p-pass streaming algorithm naturally turns into a p-round communication protocol, where a round, it depends on how you define it, but one natural definition is when each player gets to send one message, that constitutes one round. The messages they send each other are, of course, just the internal state of the data stream algorithm. So any communication lower bound translates into a stream lower bound. Usually the communication problem that results this way by cutting up the stream isn't very nice as a problem. It's not so clean. So you'll sometimes want to take a special case which you can interpret combinatorially and turn this into some clean problem about zeros and ones. Okay? All right, so without further ado, what are some communication problems that come up? So I claim that there are three fundamental communication problems that really every theoretical computer scientist, and actually every computer scientist for that matter, ought to know. Okay? And these would be index, equality, and set disjointness. And if for some reason you didn't know about these, then you will by the time I'm done. Right? You will know what it is that you absolutely should know about these problems. Now, actually, there are two more modern problems that I think have also turned out to be fundamental. So one of these is the gap Hamming distance problem, which, and the other is the L infinity problem. I will define every one of these things. Okay, so let's start by talking about index, possibly the simplest communication problem. So here we have two inputs. We have two players. Alice has a string of n bits, and Bob has an index between 1 and n. They must talk to each other and compute the index function, which is the kth bit of Alice's string. Okay, the parties may use randomization, so the answer only needs to be correct with high probability. So we think of two measures of success for the problem, or rather two cost measures. So one is a straight up communication cost, which is the number of bits exchanged in a worst case run. You want to minimize this, of course. And the other is the error probability, which is the worst case over inputs of the probability that you give the wrong answer. You want to minimize that too, or maybe make it less than some threshold epsilon. Okay, so the astute among you, and of course people who've seen this before, will notice that if Alice and Bob were really to interact amongst themselves, then there's an easy solution where Bob sends the index over to Alice. After all, Bob has only log n bits of information with him, and Alice has n, so Alice has the harder task if she has to communicate to Bob. So, to make the problem interesting, I, let's say, require that communication only go from Alice to Bob. And in this case, you can basically show that there is nothing non-trivial that Alice can do. I mean, Alice can, of course, send her entire input over to Bob at a cost of n bits, and that's pretty much the best you can do. This is not a hard theorem to show as communication complexity theorems go. In fact, it's an exercise. It's, to be precise, exercise 4.20 in the textbook of Koshilevitz and Nissan. It's also a paper of Ablayev. So Ablayev's paper actually shows a little bit more than what I've just stated. You can enhance the problem to this thing called augmented index. In the augmented index problem, a little birdie tells Bob the first k minus 1 bits of x. Note that he wants the kth bit of x. So in some sense, this information should be useless, but, well, it requires a proof, and you can prove this. Right? Okay, and I'm not going to go into how exactly you prove this. I want to say why this is important for streaming. So I claim this is very important. This is a problem that will handle a whole bunch of streaming lower bounds right away. So I'll give you an example. So let's return to the Munro-Patterson problem, which is finding the median of a stream. So you can do the following reduction from index. Okay, so you're given an index instance, x and k. Alice constructs the following stream, which is n minus 1 copies of negative infinity, followed by the numbers 2, 4, 6, 8, etc., but with the lower order bit tweaked according to the corresponding bit of x. Right, so I'll refer to this as embedding a bit string in the stream. Okay, we'll see this idea come up again. Now, if you look at only Alice's input, then by construction, the median is exactly that number 2 plus x1. Right? Now, when Bob inserts an appropriate number of copies of plus infinity to the stream, then the median starts shifting to the right. Right? In fact, if he inserts the right number of copies, then the median is exactly the number corresponding to the desired bit. And since I've encoded the bit in the lower order bit of this number, then all I need to do is figure out if the median is odd or not. Okay? And I've solved index. So because I've solved index, it means that I must have communicated order n bits. Therefore, we get the theorem that median finding requires order n space. Okay? So you might think that was too simple. Yeah, well, it was. But actually, this type of idea and increasingly sophisticated versions of this idea apply to a huge number of problems in data streams. I mean, I can't begin to summarize them all. I've just put a few random examples down here that I know about well. Okay. So I'm not about to go into these things, but you can sort of vaguely see what these are, right? You can talk about more than one pass. This talked about only one pass. You can talk about random order streams. By the way, the references that I've put down are just in, there's some matching between the references and the results, and I'm not indicating what it is. Right, okay, so that's the beginning. Here's another application of index that's kind of different from all these sequence type problems. So here's a graph problem. So suppose you wanted to decide whether or not your input graph stream describes a connected graph. Okay? So here's something you can do. So take your index instance and encode it as a graph problem as follows. So the vertices are fixed like this. You have ST and then you have n vertices, 1 up to n. Alice throws in edges that correspond to the ones in her bit string. Bob throws in all possible edges on the right, except for the one that corresponds to his index. Okay, so in this case, except for the edge from 5 to t, he includes all else. You will notice that the vertex 5 is disconnected from the rest of the graph, and it is precisely because there is no edge from 5 to t, which is precisely because because Alice has a 0 in the 5th position. All right. So this fairly easy reduction shows you that connectivity requires omega n space, at least if you use a single pass, right? So actually this omega n is a fairly general phenomenon for a lot of graph problems. You can do simple reductions like this, which show that almost all interesting graph problems basically require omega n amount of space. So you can't really shoot for sublinear in n amount of space. Though, of course, you could shoot for an amount of space that's like n times some small function of n. Okay? And this is pretty much the realm of semi-streaming algorithms, which is a big topic of study. I suppose that triangle counting is one of those few exceptions where you can sometimes do something better in space sublinear in terms of number of vertices. Okay. All right. Let's move on to a different communication problem. This is the equality problem. So the equality problem, Alice and Bob both have n-bit strings, and the question is whether these strings are the same or not. It's as simple as that. All right, so here we have a log n bit communication protocol using a very simple fingerprinting idea. I think to this crowd I don't need to explain what fingerprinting is, so I'll leave it at that. In fact, you can get it down to just constant communication if you assume a shared random source. But if you did not have randomness, then this problem provably needs omega n communication. Right? Actually, you can see I can remove the omega. I can say that you need exactly n bits of communication. Okay, so this shows us that randomization is important to solve the equality problem, and this in turn allows us to prove for a number of data stream situations that randomization is unavoidable. Okay, so here's one classic application. So these are frequency moments again, which Graham defined for us this morning. I'll redefine them. The little f sub j counts the number of occurrences of the item j in the stream, and the sum of the kth powers of these frequencies is the kth frequency moment, denoted capital F to the k, capital F sub k. All right, an important special case is f0, which is the number of distinct elements in the stream, or the cardinality of your set. So here's a reduction from the equality problem to determining the quantity f0, right? This is actually that same idea of embedding the bit string into the stream in the lower order bit, except that instead of producing a stream of integers, I'm now producing a stream of pairs of integers. It doesn't really matter, I can re-encode these things as integers if I wish, but for the purposes of problems like frequency moment, I don't care that the elements themselves are integers, since I'm only counting their frequencies. All right, so it's written symbolically below. You can see what it does. It's easy to check that the number of elements in the combined stream is basically n, one for each position, plus the number of places where the bit strings x and y differ. Right? So where x has a 1 and y has a 0, I have two distinct elements in the stream. Otherwise, I have only one element. Okay, so delta xy denotes this number. This is called the Hamming distance between x and y. So this means that if I solve f0, then I've basically solved the equality problem. So I'm claiming here that if I have a good approximation for f0, this also solves the equality problem. There's a slight problem with that, not quite. Suppose x and y differed in only one position. Then I would pretty much have to get a very good approximation for f0, right? I would have to approximate f0 to within plus minus 1, which is the same as determining it exactly. Fortunately, there's an easy trick to handle this. So what we really need is to make sure that whenever x and y are not equal, somehow their Hamming distance magically is rather high, right? And I'm sure you know how to do that. You just apply an error correcting code, and that ensures this property. Okay, so this shows that if you wanted to approximate, say, the number of distinct elements, or really any frequency moment, then you need to use randomization. All right, so those are the first two fundamental problems. The third is the set disjointness problem. Now let me point out that index captures a certain type of hardness. Index captures the hardness of doing things in one pass. Equality captures the hardness of doing things deterministically. Right? Now there are times when you think your problem is hard despite randomness and despite using multiple passes. What do you do then? Then you bring out the heavy hammer of set disjointness. All right, so this is the set disjointness problem. Alice and Bob have n-bit strings, which you can view as subsets of 1 up to n. And the question is, are these sets disjoint? Right? So the disjointness function is, say, 1 if the sets intersect and 0 otherwise. I mean, historically, this is how it's been denoted. It's a bit unfortunate. It should probably be called non-disjointness. But anyway, that's what it is. Here's a different view of that same problem. You can write Alice's input on top of Bob's, and now you have a 2 by n matrix. And the problem can be thought of as distinguishing between the following two cases. So in case 0, every column has weight at most 1, meaning there's at most a single 1 in every column. And in the other case, in case 1, one of the columns has weight 2, indicating an intersection between the sets. Otherwise, the rest have weight at most 1. So if you think about it, this is actually a special case of the disjointness problem where I'm promised a lot about the input. Nevertheless, you can show that this version of disjointness is also hard. It requires omega n communication. This is even if you have randomness and no matter how much interaction you use. Okay? It's a classic result in communication complexity. But for the purposes of data streams, you need a further extension of this, which is if you extend this problem from 2 players to t players in the natural way, just replace the number 2 in the statement of the problem with t, then you get the t-party disjointness problem, whose communication complexity grows like n over t. Okay? This last result actually is the end of a pretty long series of papers, which I've just indicated out there. Now here's one basic application of disjointness. This one's going to use only 2 parties. Okay, so we come back to the graph connectedness problem, for which we showed a 1-pass lower bound. We can show that a multi-pass lower bound also holds. Okay, so we just use a different reduction. We construct a different graph. So now Alice has a string and Bob has a string, to be thought of as sets, if you like. So Alice introduces edges from S to I whenever I is not in her set. Okay? And Bob introduces edges from J to T whenever J is not in his set. The observation is that this graph is connected if and only if the sets are disjoint. Okay? Because if there's an element in common between X and Y, then neither Alice nor Bob would have introduced the appropriate edge. For example, 5 is an intersection in the given example, and neither Alice nor Bob introduces an edge to vertex 5, right? So it's disconnected. Okay, that's all there is to it. It really is that simple. Now the classic application of disjointness is lower bounds for the estimation of frequency moments. So first let me say something about what upper bounds are known. So it's known that for k between 0 and 2, this problem is approximable in space that's about 1 over epsilon squared times some log factors. For k bigger or equal to 2, the space starts growing kind of polynomially in the length of the stream. Right? So there is a dichotomy in the algorithms, and this dichotomy is in fact real. So you can prove a lower bound that shows that for k at least 2, you do need a space m to the 1 minus 2 over k. Right? And this is using the t-party disjointness result that I just put on the previous slide, together with a reduction that's due to Alon, Matthias, Sagiri. Right? So so they didn't get this result. They got a weaker result, but after the optimum communication bound for disjointness, we have the result that is shown here. Okay, so they just reduced from disjointness with a large number of players. So note the innovativeness here, which is using a number of players that actually depends on the input length. Once I tell you this, you can go home and do this reduction yourself. It's very easy. So all you do is convert each set into a stream and observe that if the sets are disjoint, like I said, then every frequency is at most a 1. So there's the frequency moment is going to be low. Or else, if in case 1, the sets intersect. I'm sorry, it should say sets intersect in case 1. In this case, there is an element with rather high frequency, which leads to a very high value of fk. So there's enough of a gap that approximating fk will distinguish the two cases. Okay. Everything I've said so far, by the way, is pretty old hat to somebody who works on data stream, lower bound, and so on. Now let's get to somewhat more modern problems. So the gap Hamming distance problem is the following communication problem, and I'm saying that this is another fundamental communication problem. So here Alice and Bob again have n bit strings, and the I guess you don't want to view them as subsets of n. Sorry, it's a carryover from the previous slide. The function in this case is the gap Hamming distance function, or GHD. It's defined as 0 if x and y are close in Hamming distance, and 1 if they're far in Hamming distance, where close means square root n below the expectation, n over 2. So if you think of x and y as being uniform random strings, the expected distance is n over 2. So we're talking about one standard deviation below that versus one standard deviation above that. Right? And let's say we don't care if the distance lies kind of in the middle. Right? So this is an easier problem than just deciding one between above and below a sharp threshold. Okay, so result of mine and Regev is that this communication problem needs omega n work, randomized, multipass, whatever. And this gives us another, this gives us another lower bound for this FK approximation, among other things. So notice that the previous result only talked about the dependence of the space on M. Okay, there's also this dependence on epsilon, right? You see this 1 over epsilon squared in the upper bound, and actually you probably encountered 1 over epsilon squared in several data stream upper bounds, including some mentioned in talks this morning. So the theorem that you can get is that this 1 over epsilon squared is inevitable, and the reason it comes up somehow is because many of these data stream problems incorporate a solution to gap Hamming. So for instance, here's how, say, distinct elements incorporates a solution. You just use the exact same reduction as before, right? And observe the fact that the number of elements is equal to n plus the Hamming distance, which we had observed before. And that's basically it, right? And if you want one more piece of information, then the 2 in the exponent of 1 over epsilon squared is directly related to the square root n, which appears in gap Hamming distance. Okay. All right. Final of the basic problems is the L infinity problem. Right. So this is the statement of the problem. So here Alice and Bob have strings of length n, or vectors of length n, with entries in 1 up to m for some large quantity m. Right. So these are not bit strings anymore; they're strings of integers. So the L infinity distance between the vectors is defined in the usual way. So L infinity is the max difference between xi and xi minus yi over all I. Right. Now you need to distinguish between the case when the L infinity distance is at most a 1, meaning that x and y are roughly equal on every coordinate, versus the L infinity distance is m minus 1, which means there exists a coordinate where the difference is as high as m minus 1, it's as high as it can be. Okay, so in a paper of Bar-Yosef et al., they show that the complexity of this problem scales as linear in n. It also does degrade with m. As you can imagine, once m becomes very large, then the 2 cases, the 0 case and the 1 case, are kind of further apart. So it should be easier to distinguish between them. All right, so that's the right behavior, n over m squared. So this also has many applications, and a typical application is lower bounds for estimating norms for data streams with deletions. Okay, so data streams with deletions, if you don't like deletions, they come up naturally if you want to do something like, what is the difference between yesterday's IP traffic and today's IP traffic? So let's say you've collected something about, so you can imagine this as inserting all of yesterday's IP traffic and then deleting off today's IP traffic, and therefore getting a different stream. And any kind of interesting thing you want to estimate for that will, at some level, be solving a version of the L infinity problem. Yeah. Okay, so that's the basic biased guided tour through communication complexity problems. I've only mentioned the simple ones, of course. As I said, that's all I'm going to mention. Now a word about how we actually go about proving communication lower bounds. You see, so far all I've said is you can reduce one of these communication problems to your data stream problem, right? Actually, there's a whole book out there, Communication Complexity by Kushilevitz and Nissan, which is entirely about how you prove lower bounds on communication. I'm not going to be able to summarize anything meaningful in a single slide. I should mention, though, that the textbook already is kind of outdated despite its brilliance, because there's a whole bunch of new techniques that haven't made it into the book, which is close to 2 decades old at this point. Now, one very common theme that comes up in these new style lower bounds is what's called direct sum. So a direct sum result is something of the following form. So you take a small lower bound, right? By small lower bound, I mean something like, Alice and Bob's inputs are of some constant size, right? If they're of constant size, then, well, you should have a constant lower bound. Usually all you need to do to prove this is that the problem isn't completely trivial and cannot be solved without communication. All right, so you have a constant lower bound. Now scale up this lower bound by saying something along the lines of, as the input size grows by a factor of n, then the communication required also grows by a factor close to n, right? If this happens, then you say that the problem demonstrates direct sum behavior. Okay. I should mention that this isn't a trivial thing to prove at all, far from it. And there are situations where it's not true even, so that's why it's hard. But one way in which results like this can be proven are to not count the number of bits communicated between Alice and Bob, but instead to look at the mutual information between the input and the messages. So mutual information being a standard concept from information theory. And this paradigm is called the information complexity paradigm. When it applies, it's very easy to prove lower bounds. I will not say more about this. That's sort of a talk on its own, trying to explain this paradigm. But if any of you is coming to Stock in a week's time, I'm scheduled to give a talk on that there. So you can consider that part 2 of this talk. All right. At any rate, with some information theoretic ideas, we can actually handle all 5 basic communication problems and get all of those communication results that I claimed. Okay. I should mention though that it's not quite so simple as saying that you can view your problem as an n-fold blow up of a simpler problem and therefore the results follow. Sometimes you need to argue this blow up very carefully and you need often some deep mathematics in addition. So just to give you an example, this is I think the deepest mathematics that has come up so far in any of these problems. So it comes up in the context of the gap Hamming distance problem, and it requires, for example, this theorem, which you can take home as a little nugget. So if you have a set with high Gaussian volume in Rn, okay, so it's an n-dimensional set with high Gaussian volume. I'm not saying exactly what high is, I'm not quantifying things precisely, but if you do, then such a set needs to be thick along several directions. Where thick means if you project along that direction, then you don't have a very concentrated set. Intuitive maybe, but there's all sorts of ifs and buts. For example, I didn't say that the directions are actually orthogonal. They're near orthogonal only, and that sort of makes all the difference. It makes this thing rather hairy to prove. So this really can be seen as a result in functional analysis. So we had to dive into this to get our bound. Okay, so these were just the basics. As I said already, these 5 communication problems, if you understand them well and master them, you can derive a whole bunch of results about data streams. Here's a sampling of some other results that you can derive. Very, very nice paper of Guha et al. That I should put in a plug for. So they looked at information divergences, so differences between probability distributions, and there's various ways to measure difference between probability distributions. So they showed that with the 2 natural exceptions of L1 and L2, it's impossible to build small sketches for these. So basically giving you a complete theory of what's doable. And they use reductions. At the end of the day, they're using reductions from disjointness and gap Hamming. If you wanted to see an example of a very sophisticated reduction in this space, then I would recommend the lower bound for graph diameter estimation from Feigenbaum et al. This is also a reduction from index, but it's quite a challenge to find it. I mean, I bet that if I told you reduce from index and sent you home and you hadn't seen this paper before, that you couldn't come up with this quickly. It's a sophisticated reduction. Sometimes you need to generalize the problem in some unexpected ways. So there's some recent work I had with Graham and Andrew on probabilistic checking of data structures. And these also involve reductions basically from version of index that involves many players. Okay, so I won't say much more about how we can make a problem that looks like index that involves many players, but you can, and that's what gives you the result. Let me end by just putting up 2 of my favorite open problems in this space. So for estimating the length of the longest increasing subsequence of a data stream, we know that the deterministic complexity is order root m, We don't know anything about its randomized complexity. It could be order root m, it could be order log m. Right? It's wide open, and I think this is a very interesting open question. A different kind of open question, which is probably more appealing to theorists, is can we get some very generally applicable direct sum results in communication complexity? I think this is a bit of a holy grail now in communication complexity. There's a lot of people seeking it, but if we got there, then I can imagine a unified framework for several data stream lower bounds, more unified than there is right now. All right, thanks. I'll stop with that.